Alright, so now we want to talk about half-lives. A half-life is the time that it takes for one half of the nuclei of a radioisotope to decay. After each half-life, half of that existing radioactive atom or atoms, half of them have decayed into a different element. So when you have a sample, okay, this is where it gets a little bit confusing. So after one half-life, okay, you cut it in half. Woo! Okay. After two half-lives, cut it in half. 3 half-lives, cut it in half. 4 half-lives, cut it in half again. And so on and so forth. Technically speaking, you're never going to run out, right? It's just going to keep getting smaller and smaller and smaller. But here's the thing. First of all, it doesn't look like this. Okay, if you have a rock and it's decaying radioactive particle, if it's giving off radiation, all this is not what it looks like. It's not like, okay, the left side of the rock decays. It's uniform, right? It's more like you have this rock and then, like half of the particles decay, and then the next time half of those particles decay, and so on and so forth. Alright? So it's spread out. And the other thing is that when something decays, it's not like it decays and then just falls off. Okay? It's turning into something else. So just because it's decaying doesn't mean like the rock is disappearing. It means that it's a different type of atom now. It's a different element than it was to start. So this is kind of what a curve would look like. So after one half-life, you're going to have 50%. After two half-lives, now you're going to have 25%, which is a fourth of what you started with. And then 12 and a half, and so on and so forth. So it's always half of what was there at the beginning of the half-life you're focusing on. Here are some common half-lives. If we're talking about using radiation to date something, you typically try to pick a half-life that will be conducive to the time that you're measuring. So, if you're trying to measure something that's really, 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 really old, like in millions of years or something, you can't use carbon-14 very well because it's, or billions of years. You don't want to do that because this is in the thousands of years. Now, of course, you could try, I guess, but it's just not as easy. Whereas if you're looking at like billions of years, now you're talking uranium-238 because its half-life is that long. So this is kind of what happens. If you have uranium, it's going to eventually decay into thorium and so on and so forth, and it just keeps going. So there's always, there's always a track of where it's been, and then eventually it's going to get to something that's stable, and it's going to stop there. So eventually, almost everything will turn into lead, but it takes a very long time. Notice that not all the half-lives are the same. You have a really long half-life, then you have one that's 25 days, then 6 hours, and so on and so forth. So there's longer periods where, it might be thorium-230 for a long time, and so on and so forth. Some fun facts. Uranium used to be used in like that Fiesta-ware stuff to get the brightly colored dishes like orange and reds. The salt substitute, where you use potassium instead of sodium, that is radioactive. Smoke detectors, I'll show you a video in a little bit, shows you how this works. Smoke detectors, actually, a lot of them use a little bit of americium, and that, if the smoke stops that particle from going and like deflects it, then all of a sudden you'll get the alarm going off. So, an example of doing half-life problems. If you have this starting mass, the half-life is 5,730 years. How long is 3 half-lives? Well, 3 half-lives is going to be 5,730 years times 3. Okay. How many grams will remain at the end of 3 half-lives? Well, you have 2 times 10 to the negative 12. Okay. So after 1 half-life, you're going to have 1 times 10 to the negative 12. It's 1 half-life. After the second half-life, you're going to have 0.5 times 10 to the negative 12. And after the third half-life, you'll have 0.25 times 10 to the negative 12, which is the same thing as 2.5 times 10 to the negative 13th. So hopefully that makes sense. ask me some questions. Well, why don't we go ahead and do this one too? What's the mass of manganese 56 in a 1 milligram sample of the isotope at the end of 10.4 hours if the half-life is 2.6? Well, to find out how many half-lives there were, you take 10.4 divided by 2.6, which means there's 4 half-lives. So if you start with a 1 milligram sample, after 1 half-life, you're going to have 0.5 milligrams. After 2 half-lives, you're going to have 0.25 milligrams. After 3 half-lives, you're going to have 0.125 milligrams. Okay, and then after that, you do 0.125 and divide that again, you're going to get 0.0625 milligrams, and that's what's going to be left over. So, there you go.